Hi everyone, my name is Don Gamage and I'm a second year PhD student at University of Auckland. Today I'm going to talk about my paper ID 2122, which is about a distributed coordinated consensus control for multi-energy storage of DC microgrid. Let's look at the background of this paper. So as you can see on the top left diagram, I have a multiple battery system connected according to the undirected graph, undirected communication graph, which is shown just above these in this figure. And so we have connected a number of batteries in parallel mode. And also as a main energy, I'm using the PV combination of MPPT control algorithm as well, so which will provide you the maximum power relative to the corresponding irradiance level. Um, and I have also used the supercapacitor, which helps for the transient fluctuations. So in that case, actually give the less stress on the batteries, and that will eventually increase the lifespan of the battery assays. So in this paper, actually, we mainly looking at the control perspective, which is about the consensus control. So as you can see on the bottom diagram, I have this implemented consensus control to give the reference currents for the individual batteries. Um, as a local controller, I'm using the normal PI controller. Um, so in this proposed controller, it gives consensus among the state of charge, power, and energy of the of all these energy storage systems, respective to the deficit and excess mode of operation. As a closed loop dynamic, you can find in this equation, so which is like x dot equals x plus bu system, and in this case my input is c, k, and this term. So this k actually can be found using the arithmetic Ricardo equation. The results of the convergence um, can be found on figure 5 and figure 6. So as you can see, state of charge of all the batteries converge um, at around this time, and also the power and the convergence of energy also converge at the corresponding times. So main thing we want to emphasis on this one, like when the Q value is going high, the convergence rate is increased. So as you can see on the figure 6, the high Q value will give the faster convergence of the state of charge, power, and also the energy. Um, so, um, um, so although there was a overshoot, um, tiny bit of overshoot showing in the high Q values, but still the faster convergence can be achieved using the high Q values, which is really important in the field of applications. So that's the convergent results of the consensus controller. And so this is the hybrid energy storage system characteristics. So the battery current is represented on the far left diagram. So as you can see, from T1 to T2, the battery is charging. So which is like the irradiance change. Um, irradiance value is increased, and then the generation increased from the PV. So, and also vice versa, T3 to T4, the battery is discharging because the demand rate is going up. And the middle graph, 7b, represent the supercapacitor characteristics. So as you can see, the current fluctuations represents the transients points of all the uh, um, demand changes, um, and, and similarly 7C represent the DC bus link voltage. So you can see it's always regulates at the 48 volt, regardless the deficit and excess mode of operations. Yes, and then the conclusion was this proposed controller achieves the consensus of state of charge, power, and energy of multi-battery systems. So for high Q and K values, of course, we saw the convergence rate is faster, and the supercapacitor's transient response actually helps to reduce the stress on the battery, and that will give the long lifespan in the long run for the battery as well. So in future, this experiment can be further developed using different types of batteries, such as flow batteries, etc. So, and then compare the results among them as well. So that's the end of the presentation. Thank you for listening.